Test, test, test. Test, test. Hey, good morning. Let's get started. All right. So we started a new topic on system modeling. And this topic, the idea, the ultimate goal of this part of the topic is to derive a system equation, okay? Any kind of equation, as simple as a linear system, a linear equation, or as more complicated as a nonlinear equation, or in our case for this class, as you will see, we mostly will derive a set of a linear differential equation, right? So the idea is to get something so that we can use mathematically, so that we can use it to obtain the system dynamics or characteristics. Okay. In order to do that, we looked at essentially different we look at different physics laws. So those are essentially the principles that you can use to construct a system model. We also started looking at individual components of a system. How do we model each one of them? So then if we have a connection of all the individual components, so we can put all the equations together, right? So we looked at electrical components. R, C, L. It was a very simple one: resistor, capacitor, and inductor. Okay. So how do we model that? Okay. So this is what we did in the previous lecture. Now today, let's continue this. Let's look at some mechanical components. First component is mechanical spring. So we started on the mechanical spring already. So let's do that a little bit again here. Okay. And mechanical spring means you have a spring, like it's a components which can extend or being compressed. And we use the K to represent the so-called spring stiffness. Essentially, it's a constant, okay, representing how difficult is it to elongate it or to compress it. And to model this, we usually have two ends, but if this is the case here, this X here, right, represent the displacement of the free end. And we have specifically said the X here, right, is called displacement or deflection, okay? But you have to be very clear, this is a quantity with respect to the equilibrium position. Or location. So where is the equilibrium? That really depends. When you have a system and you let it settle, then that settled state, right, is the equilibrium state. So let's say this is probably equilibrium. We don't really indicate where the equilibrium is in the drawing. We can just draw the X. Right, so then you would know that this is reference to certain equilibrium position. Okay. Another thing I want to emphasize is, you see the drawing here, right? When we draw this displacement x, we draw an arrow sign here, okay, attached to this free end. So this arrow here, okay, so the drawing, this one here, this, you got to be clear. This is just a reference direction for x, okay, reference direction for x. So what does reference direction mean? When you do things, right? When we do things, anything basically, we always have to establish a reference first. So for example, we say going to the west is considered as a positive, right? So okay, that's basically reference. Then the next time you say somebody going to the east, okay, then the guy mathematically going to the negative side, right? So that's what reference means. So when we draw the arrow at here, saying that's the reference, basically means if you have a movement, right, to the right side of this equilibrium position, which is basically the direction indicated by the arrow, then you got a positive displacement x. Of course, if the x or the free end is somewhere around this side, then you got a negative x basically, right? That's the reference, because that x is an opposite direction of the reference arrow. So I want to be clear basically is I got a lot of questions in the past is when you draw an arrow, does that mean that x cannot actually go to this side, or does that mean the spring cannot move right to the other direction? So that's not what this means. Okay, so this just means that there's a reference direction. Okay? The actual motion certainly could be in any directions. To describe the spring, we use the Hooke's law. F is the amount of force, or we call that restoring force, generated by the spring. So as you can clearly see, the restoring force, right, is in the opposite direction of this x, which is the displacement with respect to the equilibrium. Okay. So opposite to the deflection x. So essentially, this force exists, okay? And especially if you attach an object to the ends of the spring, then that object will feel the force. So that force will be exerted to any mass or object attached to the free end. And that force, right, exerted to the mass will be determined by this quantity. So if you got a positive x, then negative means it's the force exerted is to the opposite direction of the x. So we'll see that when we draw a free body diagram later. Okay. Yeah. So that's a simple case when you have just one end free and one end is fixed. A little bit more complicated case, which is also very common, is that you have both ends are free to move for a spring. Then in this case, as usual, we indicate the displacement of the both free ends using x1 and x2. And then we draw this so-called reference direction for the displacement. So now you can ask yourself, the x1 and x2, the definition of that, their displacement with the corresponding equilibrium position. And of course, both ends not necessarily can be elongated to the right. It could be whether it's stretched or compressed, right? So for example, if this side go this way, it's compressed. If this side go this way, it's actually considered as a stretch, right, for these ends. Okay. So how they actually goes, we don't know, right? So it really depends on the motion. Okay? But in your mind, you should know it's allowed to do both directions of motion. So then you can certainly attach certain mass to either side of the spring. Okay, so say you can attach M1 and M2, okay, two masses attached to the ends of the spring. Okay. So now let's see, if I ask is, how can I draw the free body diagram, for example, say for this M2? All right, so in order to derive an equation of motion using Newton's second law, okay, we need a free body diagram. We need to get the total external force and then apply the Newton's second law, right? So let's say I have M2 attached over here. So this is the everything we have for now, right? So what would be the external force acting on this M2? Okay, so there's no external force applied by any user. So the only external force will come from the spring, right? So the question is, how much force is that? Okay, so then you go back to basically the Hooke's law, which is right here. Okay, so F equal to negative kx, but this one applies to one end is fixed, one end is free. So then for both ends are free to move, then we're looking at is what is the restoring force, right, from the spring when both ends are free. So basically what we did in the previous lecture is temporarily you can consider this side is fixed. Then your restoring force is negative k x1, right, if this side is fixed. And now you let this side go, you can see now, okay, x go this way, you stretch that a little bit to this side, and x2 go this way, and then the spring, this side is stretched, this side is being compressed a little bit, right, according to the drawing, okay? So then the total deflection is x1 minus x2. So that will be the restoring force, right, of generated by this spring right here. Then what direction is this restoring force then? The negative sign, the direction goes to, if x1 goes this way, then the F go which way? The opposite, right? So then for M2 at here, which feels this restoring force, so then what you draw is, you just draw this F at here, but this time when you draw the F, when you label this force, should I keep the negative sign or should I get rid of the negative sign now? What should I do with the negative sign? Should I label this force as negative k x1 minus x2? Now it's big. Why do? Okay, so I think a lot of people say I should get rid of the negative sign. So why should I get rid of the negative sign now? Exactly, right? Because I have already drawn the arrow pointing to this negative side of this reference x. So I don't need the negative anymore when I draw the arrow over here, because you know this is pointing to this way now. Okay. So the next time when you apply this, you know this is in the opposite direction of x. So you still should know the opposite, the reference direction is still this way, right? Okay. So there's a little bit difference mathematically how you write it down and mathematically how you label it to a free body diagram. And this is basically a free body diagram. Good. Okay. So and now it's pretty straightforward. There's only one single spring attached to this and one single external force due to the spring, right? So we're gonna put a few other things together, okay, to make it a little more complicated. Okay, so that's mechanical spring, right? So now let's take a look at the next one, mechanical damper. as I have probably mentioned, the spring damper and the mass system, right, can be very much illustrated by a car suspension system or even by the hinge of this door at this classroom. Okay. So dampers symbol we can use this symbol here. So you have a basically like a opened box, and then in the middle there is like a valve motion, right? So it's allowed to move, okay? Like a plate. Okay? And what's in the damper typically there's some viscous fluid. Okay? So basically there's fluid in it, okay, and serving as the damping material. So you can use this symbol and use the B at here to represent a so-called damping constant. Damping constant of the coefficient of viscous okay. So same as the mechanical spring, so there are always two ends for a damper. Okay, so we can start with one fixed, one free end, okay, for this damper, and then we can label the displacement of this free end as x. Okay, very much like the spring. So if you stretch this damper, right, then what you feel is you will feel force trying to pull you back, a little bit like a spring, basically. Okay, but this time the force exerted from the damper is proportional to x dot, not to the x anymore. Like spring, right? It's proportional to the x, the inverse proportional. But this time it's proportional to the x dot, which is the velocity, basically. So now basically how fast you're putting it, and give you a higher value of the restoring force. So that's the nature of the mechanical damper. And again, right, this F here is the restoring force in the opposite direction of velocity. So that's the nature of a damper here. So now let's look at just like spring. What if I have both ends free to move? Draw the reference direction for the both ends of the damper and write down the B representing the damper. Okay. So you could definitely attach two different mass, okay, on either side of the damper. So this can be M1, this can be M2. So then the amount of force exerted by the damper, okay, due to the both ends are free, will be slightly different from this formula. Okay. Let's write it down here. Now, because I have M1 and M2, one is on the left side, one is on the right side. Actually, I should probably go back to this example because I only draw the free body diagram for M1. You know what? Let me just, maybe I should want one more free body diagram here. What would be the free body diagram for M1? Right. What will be the free body diagram for M1 then? Yes. So K, so first tell me the number. K what? Okay, so which direction of arrow you should draw? To the to this direction or to that direction? Okay, so you're saying is to this direction, right? Anybody disagree? Yes. Okay, so should go this way. Okay, so well, and there are two ways, right? Which way should it be? So think about the concept, right? This F is the restoring force in the opposite direction of the displacement of M1. What is the displacement direction for M1? Indicate by which variable? X2, right? So if you have to get in the details, X2 goes this way, okay? So if you fix this side, where should that restoring force pointing to? Is this still this side way? No? If you fix this side, and then you move this end a little bit to the right, to the right, right? Yeah. The restoring force should be that way, right? Exactly. And of course, we all talking about the reference here. The actual movement X2 could be the other way, but I'm talking about reference here, okay? Yeah. So if it's a fix this, the force, you just said it just should pointing this way. And it is due to the compress of the spring given by the X2. So now the other side of the spring, you're allowed to move, and then you stretch a little bit. So maybe not as much compressed as before anymore, right? So then you should minus this X1 to take off some of the compression, because X1 is exerting as a elongation. But the force maybe is, according to this, is still in the opposite direction of X2, right? The restoring force. So your force, your width of force you draw here should be still sketched as the negative direction of your X2 at here. However, you certainly can argue, could the force actually point this way? Yes, it can. So only when what? When X2 is actually less than X1, right? Your calculation X2 less than, then the actual direction force is pointing this way. But whatever we draw at it here, okay, whatever we draw here is all about the reference. It's not about the actual calculation. Is that good? Okay, so this is important because as you're going to see next to when we have a 2 degree of freedom to draw a free body diagram, you got to have to be able to draw the direction correctly and also label this, right, as it's supposed to be. Okay, so let's get back to the damper here, right? Let's do exactly the same thing. Okay, let's do the exact same thing. So let's say for objects on the right, okay, for object on the right, which is M2 at here. For object on the right, how much restoring force is exerted by the damper? Okay, so we pretty much use exactly the same analogy as spring in here. So you can temporarily fix one end. Okay. If you fix one end, your force equal to negative B x1 dot. Right? If there's one end is fixed, then that's just negative B x1 dot. It's in the opposite direction of x1 dot, the velocity. And now the other end is free to move. So x1 dot minus x2 dot, like the x1 minus x2. So if I have an object m2 at here, okay, and there's only only force we can feel, which is the restoring force. So then you need to draw the force pointing this way at here. Now you get a B x1 dot minus x2 dot. Okay, so you know what? Maybe I should a little bit be careful here. Let's be very rigorous because I draw the F right here. So I shouldn't draw the F. I should probably just label this quantity of the vector, because the actual F is in opposite direction of x2. So what we really carry is just the magnitude of this vector here, right? Yeah. Just like this one here, the magnitude of this force, okay, exerting on this M2 is B of x1 minus x2, x1 dot minus x2 dot. Good. So what will be the, how about object on the left, okay, which is M1? Then how much restoring force we're talking about? Okay, so then you do the same thing. You fix one end, then you get x2 dot, and then you minus x1 dot, right? So then this time, this M1, right, the restoring force applied to the M1 should be the opposite direction of x2 dot. So then you label this correctly. You get, this is B x2 dot minus x1 dot. Okay. All right, so that's the mass, the damper, and we also had this the spring, and we look at the became electrical already. So I think now we're ready to look at some actual examples, right? To put together those components and see what kind of equation we're going to get. Okay, so let's look at maybe one electrical and then one mechanical. Here's a very simple RC circuit. It has an input voltage Vs. It has a resistor and a capacitor. What we want to obtain is the relationship between the input and the output. And the output refer to the voltage across the capacitor. So this is RC circuit. Okay, so let's make use of what we learned for the component, each one of the components, and the law we're going to use here is the Kirchhoff current law. Right. Well, yeah, a voltage law. It doesn't really matter. Okay. So the Vs, right, should be the same if this is a current I at here. So the Vs should be the same as the current across R and C. So Vs equal to the current, the voltage across the resistor, and then the voltage across the capacitor. And we have already known that from the component, right? For capacitor, the current is related to the voltage by this relationship. The derivative of the voltage across capacitor times the capacitance give you the current going through this capacitor. So now I can substitute this I back into this equation in here. So Vs equal to Rc and dVc over dt plus Vc. Okay, so often in time, you write it. This is basically a differential equation. So you write it like this way right here, just reverse the order. And this is essentially what we call a first order differential equation, right? First order differential equation. And this equation contains the input Vs and the output Vc. And we can solve this first order differential equation. So basically, we'll see that later. So we can get a solution for Vc, and you'll see how the Vc basically changes, right? And that's a very simple example for electrical system. And let's take a look at one more electrical system. Then we can look at mechanical. Let's look at an RLC circuit. So we added an inductor added here, right, which becomes an RLC circuit. Okay, I should probably see this should be KVL law instead of KCL. All right, let's apply the KVL. You have this loop added here. So the V of t, so this time we write a V of t here. This is input, should equal to the voltage across all the components, including the resistor, the inductor, and the capacitor. Okay, so how much basically voltage across, let's say, the resistor, which is Ri, and how much across the inductor? We learned from the previous lecture is L di over dt. If the current goes through the inductor is I, then the voltage across the L is L di over dt. And the voltage across this capacitor is 1 over C, then I dt. All right, so we got an equation. In this equation here, it relates the inputs V and the current I, okay, as a differential equation. So I guess this is probably not what we want, but we probably want in this case, just like we want a relationship between the voltage and the Vc. Okay, so let's manipulate this a little bit. Let's see how we can get to that equation here. Another relationship we can make use of is the I equal to dq over dt. So the charge over this capacitor. Okay. So now I'm going to substitute this I dq over dt into the above equation that here. All right, so now I'm going to write it more or less in the order of the derivative, okay? Because this is highest order derivative. So if I plug I into this di over dt, right? Essentially, what you get is L, you get second order, right? dq square over dt square. And then I here, you get R times dq over dt. And when you plug a dq or dt into the derivative, and you get just a result of the q. So 1 over c equal to q equal to v of t. Okay, so as you can see, the way I got here is this one is v versus I. This one you go v versus q. Okay, so there are two. There's all differential equations. Okay, they're all actually second order. So you get two different differential equation. One is the input is v versus an output I, and this one is versus v versus an output, let's say a q. Right? So you could solve either one of these, you get a different response here. I guess I haven't got to the VC yet. Okay, so how do I get the VC? Let's say I, this time I'm gonna let I equal to C dVC over dt. Right? So that's the relationship between the current and the voltage across the capacitor. We use this in RC circuit. And then I'm going to substitute again back into this equation from the KCL law, or KVL. So once I substitute over there, so what do we get? So you substitute I into here, okay? And then you get LC dVC dt squared. And then RC dVC over dt. And then this one here, when you substitute into the integral here, this 1 over c cancel the c, you just get a VC back. And then V of t. With a different substitution, I get a different differential equation relating the input V to a different output variable. So this time I got a V versus VC output. So this is second order differential equation, and we have ways to solve this linear second order differential equation later. Okay, right? So this is basically what we call a model. Okay, we just created a model for this RLC circuit, and this mathematical model, which is differential equation, can be used to describe the dynamics of this system, of the simple system. All right, so now let's take a look at a mechanical example. Let's look at a mechanical system. So this system is the typical mass spring damper system. Right. So this system is drawn with a mass attached to a spring K and a damper B. At the same time, I have an external force applied to this mass M at here. Okay. And we indicate the reference displacement for this mass, okay, as X, indicating to the top position. Okay. So can you go down? Yes, you can. Okay. Yeah. So it's just in this drawing, we draw it up upwards. So same as the RLC circuits, right? The question is, what will be a system model? How can we derive a system model for this mechanical system here? So let's take a look at how we do that. Okay. to derive this model, okay, for mechanical system, first step typically you need to do is to draw a free body diagram, and your physical law is the Newton's second law in this case, right? So we need to draw the free body diagram here. And then basically when you draw the free body diagram, the question is, what are the external force that you're going to draw onto this single mass? So let's go back to the drawing at here. Let's take the obvious. You have external force apply here, which is the F, right? So let's draw this here. And you have a spring and a damper attached to this. So if there's a motion displacement X, then as we learned, there will be a restoring force coming from the spring, and there will be a restoring force coming from the damper, right? So the question is, how much restoring force coming from the spring? How much comes from the damper? And which direction shall we label that restoring force? So that's what we do, okay? So X, you go up, the restoring force should go down. Then you should have a force coming from the spring, which is Kx. Right, that quantity is in the opposite direction of the X. And you also have a restoring force coming from the damper. The quantity of that is, according to the formula for the damper, is B times X dot. And that's it, right? That's all the external force you can add to this free body diagram. So once you get the free body diagram, then the next step is you apply Newton's second law. And Newton's second law says, when you add up all the external force, it should equal to m times acceleration. I mean, this is a planar case. It's not a 3D, and all the forces either pointing up or down, right? So there's not much of a problem of vectorization. So now we go back to the free body again, okay? So when you apply the Newton's second law at here, which is mx double dots, okay? Or you write it as m dx over dt square, whichever way is fine. Okay. So let's take a look at this free body diagram. Now this is where you gotta be careful with the sign, okay? The force. For this force at here, should I put a negative or positive? Positive. Why? Because look at the way the arrow is drawn. It's in the same direction as the X. Then for this force, it's negative because this is vector draw here is in the opposite direction of the X set here. Okay, very good. Just to be a consistent, if you use the Newton's notation, then use Newton notation. If you use regular derivative, you can use regular derivative notation. Okay, don't mix them together. So finally, simplify everything. Basically, you move all the derivative terms to one end. And you get a second order differential equation like this. Okay. So this the format of this differential equation. You look at this, it's very much same as the differential equation you get from IRLC circuit. The coefficient, of course, is labeled different, and BK, and here you have LC, RC, right? And here you get RL 1 over C here, like those things. Okay. As a matter of fact, there's a connection, but we'll see if at the time we can talk a little bit about the interconnection between mechanical system and an electrical system, and what are the analogies between mechanical components and electrical components. Any question on this simple modeling example here? Now, this class is not about very complicated modeling, so you're not going to get a very complicated, modeling kind of question. Most probably what you're going to get is a system, something like this mass spring damper system, and with one end fixed mostly, or sometimes maybe the other end is free, but it shouldn't be very complicated more than that. But I do want to give you another example, which is a 2-degree of freedom mass spring damper. So why 2-degree freedom? Maybe get back to this example here. So in this example, you can see here, the mass can only move right in this one direction. So this is called a 1 degree of freedom. We write DOF, 1 degree freedom. So there's only one possible motion, right, indicated by the X. So when you have a 2 degree of freedom or of a system, and this is an example here, I'll draw it for now, M1 attached to a spring. And then it's called a K1 and B1. And then you have another one, M2. Let me see that's attached to the single spring, the K2. So you got two masses, okay, stacked on top of each other, of course separated by mechanical spring and a damper. And let's see, we have an external force applied to this M1. It's called a F of T. So now in this system, you can have a displacement describing M1. You can have a displacement describing M2. So for the whole system, this is what we call, you got 2 degrees of freedom. Right? That's indicated by the 2 variables, right? X1 and X2. Same thing. So how would we model this system, right? To come up with a second order differential equation like this one. Of course, now we're gonna, as you can imagine, we're gonna come up with a 2, right? 1 for X1 and then 1 for X2. Okay, so we follow exactly the same procedure. Draw a free body diagram first. Let's draw a free body diagram for M1. And we also draw a free body diagram for M2. And then we apply the Newton's second law. All right, so I don't have much time left, so I don't want to cram everything here. So let me give you a little bit of degree of freedom here. Can you draw the free body diagram for M1? Okay. Give it a try first, for 1 or 2 minutes. Where are the external force come from? And how much is that? How would you indicate the direction of that external force? Okay, those are the basic questions when you draw free body diagram. I'll draw the obvious ones, the F of T, right? So because of pointing down, okay, so I'll just draw it here. Okay, that's obvious, F of T. How many other external force acting on M1? Okay, good. And one must be from the spring, one must be from the damper, right? Okay. Let's draw it here. The direct did I draw the right direction? Okay, good. Restoring force in the opposite direction of X1. Because X1 is pointing down, that's why I draw to the top direction. So now the value of this force vector let's look at the spring here. Okay, this spring here. How much external force comes from the spring K1? Perfect. Perfect. Sorry, come again? Yeah. Yeah. So what? M1 and M2. What? Is that right? Okay. The force from spring equal to K1 times X1 minus X2. Why X1 minus X2? Because, right, this is the reference direction for M1, X1. This is reference direction here for the other end, which is X2. So again, if you fix this one end, right, if you consider there's nothing below here is fixed, then it's just the K1 times X1, right? But now this end is free to move, X2, so then you should X1 minus X2 here. What about the damping here? B1, use an analogy to X1 dot. So let's come back tomorrow, not tomorrow, on Friday, on the M2, and then right, the rest of things, once you've done this, the rest of things are easy. Okay. Any questions? Good, thank you.